What if I told you that two graduate students both invest $10,000, and 5 years later, one walks away with $10,000, while the other quietly ends up with over $16,000 without adding a single extra dollar? Same money, same time, completely different outcome. So what creates that gap, and more importantly, how can you control it? At the core of almost every financial decision you'll make, whether you're evaluating research funding, valuing a startup, or analyzing infrastructure, is one idea: the time value of money. And the simplest building block of that idea is a single cash flow. A single cash flow represents one sum of money moving from one point in time to another. You either take money today and project it into the future, or you take a future amount and bring it back to today. When money grows over time, it doesn't grow linearly. It grows through compounding, which means you earn interest not just on the original amount, but also on the interest you've already accumulated. In other words, you apply interest to your entire balance, your principal plus past interest. Let's break this down using the original example. At year 0, you start with your present value, P, that's your $10,000. After 1 year, the bank applies an interest rate, I. Your money grows to your original $10,000 plus $10,000 times I in interest. So after 1 year, you have P multiplied by 1 times the interest rate. Now here's the key shift. In year 2, the bank doesn't reset and calculate interest on just the original $10,000. Instead, it applies interest to your new total, the full P multiplied by 1 times the interest rate. So after 2 years, your money becomes P multiplied by 1 times the interest rate, and multiplied by 1 plus the interest rate again, or P multiplied by 1 times the interest rate squared. This pattern continues. Each year you multiply by another 1 plus I, because each period builds on the last. You stack growth on top of growth. This process leads to one of the most important equations in engineering economy. In this equation, F represents your future value, what your money becomes. P represents your present value, what you have today. I represents your interest rate per period, and N represents the number of periods. This formula lets you calculate future value in one step instead of working year by year. For example, at 10% over 5 years, $10,000 grows to $16,105.10 in a single calculation. You can also use Microsoft Excel to compute this quickly with the FV function as shown. Excel requires 2 commas between N and P because this problem doesn't include equal periodic payments. It also uses a negative sign for P to follow its cash flow convention. You treat the initial investment as an outflow and the future value as an inflow. Again, that extra $6,000 doesn't appear by chance. Compounding generates it by letting interest earn interest over time. Engineers often use shorthand for this and other similar relationship. They call 1 plus I to the n power the single sum, future worth factor, written as shown and rewriting the future worth equation as followed. Now let's try a quick example. Pause the video if you want to solve it yourself. If you got $1,762.34, you got it right. Now let's flip the problem because in practice you often work backward. Instead of asking, "What will my money become?" you ask, "How much do I need today to reach a future goal?" You answer that question using present worth, which you can solve for with the following equation. This equation lets you discount future money back to today. For example, if you want $10,000 4 years from now and your account earns 5% annually, you don't need $10,000 today. You only need about $8,227. Time and interest do part of the work for you. At its core, a single cash flow translates money across time. Compounding shows you how money grows forward. Discounting shows you what future money is worth today. Together, these ideas form the foundation of high-stakes financial decisions. You can use future worth to project outcomes and present worth to evaluate whether those outcomes justify today's investment. Now think back to those two graduate students. The difference between $10,000 and $16,000 didn't come from luck or effort. It came from understanding how money grows over time and using that knowledge. And speaking of time, thanks for spending yours watching this video. If you want to learn more about how to make money work for you, check out this playlist. I'll see you in the next one.